这个 draft 可以给
我来一个联系，你发给我吧。
这个选这个课程，你拿了这个课，大家听，好吧？
GT 多少钱啊？
啊，不咋样，然后现在给我点时间好吗？我今天给你高兴。
没有时间啊？
为什么？
啊？就没有时间啊？要开学了嘛？很多
我
东西
先把 link 加完，别的我根本不看。
你要改。嗯，我觉得另跟那个人分加完就算了。
嗯，
对，因为应该很多东西要做。是的，
那叫什么？嗯，
发给我，发给我。然后然后明天有什么？明天那个明天。Hello, testing. Okay, let's start. So, in the following week, we will try to prove that pi1 of S1 is Z. But in last class, right, we mentioned that there are paths inside S1, I guess, such that it is contractible. Okay, so I draw something like this, right? Draw something like this. So let's say there's a path here. And let's see. Okay, they can contract. Maybe use different color. Okay, they can contract to a point, but it's not really this path gets shortened, right? Okay, because because if you remember, what's the definition of a homotopy? What's the definition of homotopy? What's the definition of homotopy? When we fix x to be 0, it should be the same as, well, let's say this is gamma 1, this is gamma 2. Okay, it should be the same as gamma 0 and gamma 2. So meaning the homotopy, right? Okay, how about the other endpoint? The other endpoint is the same. So meaning this homotopy is a family of paths with the same endpoint. Correct? Okay, so if you draw like this, right? If you draw like this, it's my laser. If you draw like this, you see the endpoint keep changing. So you cannot have this kind of homotopy, but there's a way to remedy this. It's still a homotopy what I drew, but there's a homotopy between what kind of path. Well, I mean, if you want to change things, right, this one you cannot really change already because it's a point. Point is also a path, right? What path is that? A point. Constant, right? Okay, so can you imagine the ending path is a loop? Can you imagine that the ending path actually is a loop? So really what you want to do is like you could do alpha and then alpha equals. So meaning all these homotopia actually is a loop. Okay, so it's a shortening of loop until 1. Okay, okay, so maybe you say this is alpha and then this one is alpha inverse. But not necessarily alpha inverse. It could be something else. Maybe alpha inverse with a different parameterization. Okay, that's fine. Yeah. Because last time we see that different parameterization also give you the same homotopic path. Okay or not? Okay, so meaning when we say this path is contractible, right? Actually, we are talking about loops here. Okay, loops in X1. So there's one loop we're going to show that it's not contractible is this loop here. Is this looping around. Okay. Make sense? So if you walk back where it's contractible. If you walk the whole round, it's not contractible. We will actually spend a few lectures to talk about this. It's not a trivial thing. Okay. All right. Let's continue first. Okay, so let's recall what we had last time. So we have x1. Okay, let's say there's a continuous map from a topological space. So this one is the space called F. Okay, and then we said that there's a leaf. Okay, the leaf of this map to R. If this leaf here would commute with a map, what's this map here? This is a P map. So what does this P map do? It sends the time variable to e to the I. Okay. So this map should be familiar to you. Okay, actually this is the calculus 2 map. Okay, you use your line to parameterize your circle. Okay, use a line to parameterize circle. Here's something, 那么我要强身健体，早讲中。Okay. Okay, so this is what we call a lifter. Okay, if there is this. Okay, so the picture here you should imagine is I got the map into this x1 here. Okay, but I can lift to somewhere inside the real number. Okay. So this is how we're gonna think about real number. My real number is like curled up. And this is a better way to think about it. Because we will chop it into the length of x1. Okay, make sense or not? Try and think about it. Does it make sense or not? If you have something mapped into x1, right? So if you, how many of you take differential manifold this semester? 1, 2, 2, 3, 4, 4, 5, 4, 4. Okay. So if you just look around here, right, it's locally really is S1. Sorry, it's real number. Locally is R. Okay. So based on this, we'll call this a one dimension because it's locally homeomorphic to R. So this is what we're gonna trying to see. Okay. For example, let's leave some examples. So let's fix some n, and we consider the following continuous map from is a really example I borrow from calculus 2. So just unit interval here, t go to e to the 2 pi I m t. Okay, so this interval will make sure that most of the point, this map is bijection. Okay, for most of the point, only at 0, 1 they coincide. Okay, most of the point, almost for all the point is bijection. So what kind of leaf is this? So let's draw the triangle out. So we're gonna leave these to R and then down. Okay. So let's remind ourselves what this projection map is. E to the IT. Okay. And then now we're gonna send T to the E to the 2 pi INT. Okay. Right. So what do you think here? What kind of leaf I can put here so that these two things will equal? Try and think about it. What's the difference between these two? So must be the variable part, right? So what variable you should put here first to go down? Okay, to maybe let you easier to think about it. So what should I go? Where should I go to T? So what is the S you should replace so that they are equal? It's not hard to see, right? whatever other than I. What is it? 2 pi nt. Okay, so the leaf you can imagine here is t sent to 2 pi nt. Then you set s to be 2 pi nt, then e to the I pi. But this 2 pi nt here is a lift. What's the significance here? What's the significance here? Here is an exponential map. But here, what map is this? This is a you link to something, some easier map. Then linear map. Now the bottom is an exponential map. Okay, you link to something linear. A linear is good. That's why you start with linear algebra. Okay, yeah. But you also can think that there's a property about E, right? E is a periodic function. Right? E is a periodic function. Like what I teach to my calculus one last week. Sine, cos are periodic function. So E is a periodic function. So this leaf is actually not unique. Okay. How is it not unique? What can you do? Huh? Since you can shift by what? Pi or multiple of pi. Okay, you can shift the leaf by k 2 pi. There's such that k z. Okay or not? Because E will absorb the period. Okay. Any question so far? Okay, repeat after 2 pi, repeat. Because cos and sine both have period 2 pi. So far, okay? Okay, so this is a very simple example. And then this is a very specific leaf. I think if you go to a fiber bundle or stuff like that, there are more leaf. Okay. So this is a very specific case. Okay, next. So we want to discuss about this leaf. So what kind of property that does leaf have? So let W be a connected particle space. Okay. And then let F to be a continuous map again into X1 from W. And let's say they have two kind of lift. Okay, two kind of lift of F here. Okay. And then the argument is if these two lift agree at some point in the domain, then actually they have to agree everywhere. Okay, this is kind of neat. Yeah, as long as they are the same at some point, they should be the same. Okay, so the key point here, the keyword here is connected. Half is connected. Topological space also connected. Okay, so if you use this connectedness to show that they are the same. Okay, right. Actually, there's a hack here. Maybe we don't focus in general topology, but I'll tell you later. Okay, so there's a hack here about connectedness. So let's consider the following map. So let's consider their difference. Okay, we want to show that two things is the same. Right? How about showing the difference 0? Okay, let's look at their difference. Okay, there's one place at least you know this map is 0. Right, there's at least one. Okay, which one? There's at least one point you know is 0. W not right. The point they agree. We call it W not. Is it clear, huh? We call it the W not here. Okay, so by hypothesis, we have theta of W naught is 0. Okay, so they are leaf, right? So let's play around with leaf definition. Okay, so then what happens? Not that. If we apply W, apply P, the projection map, okay, on the theta W here, what do we have? Well, it's just e to the I theta W, lor. Okay. What's this definition here? So this is I to the difference between two lifts. Okay. Then it is just I to the theta tilde W times e to the minus I W. I or psi this one. Okay. And then these are just two leaf of F, right? Okay, so after you project using the triangle, right? This is just what? FW times FW inverse. Okay, using the triangle. Okay, no. So both of them is like F here, and then here's W, here's S1, and then P, and then here's R, and here is two leaf here. Okay, so you will project down. But what is this? This is element and element inverse. So it is what? 1. Yeah, identity in the X1. But this is true for all W. What does this mean? Every W sent to one place. So this is actually a constant map. Okay, this is a constant map. But so by the property of the W, right? What is d theta here? D theta here will be live inside the image of pre-image of 1. But e to the I theta, what's the pre-image of 1? When do you reach 1? Other than 0? Is a multiple of 2 pi. So your pre-image is a discrete set. It's discrete. Okay, it's a discrete set. Okay, so the point here is, so there's a lemma, maybe not gonna prove here, but I include in my notes already. So lemma here, every continuous map from F from X to Y from connected X to a discrete Y is constant. Okay, maybe we can briefly talk about it. So how do you prove this actually? So if you have a connected space, okay, but you want to map into some discrete space, okay, if you want to have a continuous map, it must be constant. Okay, you cannot send this to this point and to that point. Okay, everything must send to the same point. So how to prove this? So for example, let's say we have an image fx, okay, and then we can look at the complement. Okay, so these two are open subset of your discrete space, because this is discrete topology. Okay, so one point is open, complement also open. Okay, then you can look at the pre-image of these two. If you suppose you have a continuous function, these two set must be open. Okay, because the pre-image of an open set must be open. And they have to be disjoint, right? Because their image is different. Okay, so these two pre-image must be disjoint. Okay, but your X is connected, your domain is connected. You cannot have two disjoint open subset. Okay. Okay, so one of them must be empty. Okay, so this shows that it must be constant. So actually, there's some significant thing here happening. Imagine in real life, right? For example, you have time. Time is connected or not? Okay. For example, intelligence connected or not? You got a spectrum. Some very so high on, some less so high. Okay. And then performance. Okay. Some can do very good. Wow. Teacher ask you do what? Do everything. Some don't do or do half only, 50%. Okay. But remember, our CGPA, how many grade? Maybe 10 grade only. So how to use 10 grade to grade so many people? So this map must not be continuous. So this actually caused quite a few problems, right? Or scale up and scale down, scale everything. Not continuous. So this system is doomed to fail. Okay. So actually education is just a game. So most importantly is what we have learned. Okay. So most importantly is you make sure you learn as much as you can. Okay. Okay, let's come back. So since our W is connected, right? Okay. And then our range is discrete. Our range is discrete. So here is our range. Our range is discrete here. So it's follow that this theta here must be constant. So since W is connected, so it follows that theta must be constant. Okay, must be constant. But there's one place it vanished, right? You know there's one place it vanished, W naught. So it has to vanish everywhere. So this tell you that the two leaf is identical everywhere. Okay, so the connectedness is pretty important in this chapter here, because the item we consider is path, so connectedness is pretty, in particular path connected. Okay. Yeah, so very important. So this is a important fact. We're gonna keep using this. Okay, so if you got two map the lift up, they agree at some point, they have to be the same already. Those two things the same. This is a bit like our algebraic geometry, right? If the thing agree inside an open set, they have to be the same inside the open set. If you agree somewhere in the open set, they have to be same outside. Okay. Right. Okay, continue. Okay, let X be a topological space. 是什么病？潘纳多不可以？是啊，巴利的。哎，有一个 soluble 的，你 try 一下。不是，也是 Panadol，它是 soluble 的，它是四方形的管状比较大，那个是 for flu 的。Sorry，你 try 一下 soluble 的啊，可以 try 一下。如果没有的话，我家里有。Suppose that we have a decomposition X equals to A union B such that A and B are closed. Okay, so let's say you have X here, okay, and then you have A and B. This kind of composition are very common in this class, so please familiarize with this kind of thing, decomposing. Okay, so they are closed. Their union is X. So well, let F be a map into X1 again, X. And we supposedly we only know how to leave from A. Okay, We need to know how to live from A first. And then there's a very weird condition here, but we need to rely on this. Suppose that there exists a point P in x1. Okay, so let's draw x1 here. So there's a map here into x1. And then you know how to live on the A part. So A part you know how to live. So yes, tilde. Okay, at the A part you know how to live. So now you want to guess what we want to do here. We know how to live A part. It's not satisfying, right? We want to live at every place. Okay, so you need to tell me how to live on the B part. Okay, so let's say there exists a point in P with FB here. Okay, this is the condition to know how to live on the B part. The image of B must be missed by some point. Okay, must miss some point on P. Only then we can try and construct the leaf. Okay, it must miss somewhere. So maybe B have to stay around here, away from a point. Very special. Okay. At least you need to miss some point, okay, in your image. And then second, you might want to guess actually is about the connected thingy. Okay, we want to use the um, intersection on the domain so that we can build the lift. Okay, so that two lift is the same. Yes. Okay. You might imagine if it doesn't make, if it make P, what happens? Not injective. Okay. Yeah, not injective. Okay, so it's the injectivity problem. You come back to the same place. So yeah, let's miss some point here. Then there exists another leaf. So we abuse notation, we still call it F tilde here because we were gonna show that actually these are the two leaf. These are two two same leaf. I mean, okay? Disagree with the given leaf. Okay. Okay. So it's not a coincidence why we put F tilde again. Okay, they should be the same. Okay. Let's prove this. Let's prove this. Okay. So let's prove this. Okay. So we were gonna use all the condition. So let's pick something inside the intersection. Okay, because intersection is not empty between A, B. And there might exist some S in R such that PS will equals to P, the point you miss. Okay. Because the exponential map is surjective, right? Okay, we can find this S here. Then what we have if we put this together? So fx naught, okay, f of s naught, if is living inside f of the intersection between A and B, and then this for sure is living inside FB, right? Because A intercept B is in B. But we assume that FB is what? Living inside x1, missing out the point. Okay, so it turns out that everything inside the intersection actually won't hit P. Okay, actually won't hit P. Okay, huh? So far. Yeah, yeah. So far, okay. All right. And F tilde A, let's call it a leaf or F at the moment. Okay. Then together we would see that F tilde S naught here actually doesn't live in the P inverse of. Okay, let's see if this makes sense or not. Should we draw this? Let's say A go to X1. the next node go to P, right? And then this one is R, right? And then you go up, this one is F tilde. So you send up is F tilde. Okay? Yes, something inside the intersection. Something inside the intersection. Okay? So it shouldn't live inside the inverse of P. So this P is small p. So yeah, this is a projection. Okay? Okay, if it live inside, then you have this thing commute. If this thing commute, then Fs log should be gone. Okay, so it's not living inside the pre-image. Okay, that makes sense. So Fx not means P, the leaf also cannot go to the pre-image of P. If you go, then commute, then you'll go into P contradiction. Okay, all right. So in this case here, therefore, there exists some M in Z such that this is a property of circle. Fx naught here will live inside x plus 2 pi m, comma, x plus 2 pi m. Okay, so meaning you live in some interval. Okay, some interval. And then you won't hit the endpoint. You could choose such that you miss the endpoint. Okay, no. Okay, so this S, remember this S is something that map to this P. So you just around there, around P, because you don't hit P, must be somewhere. Okay. And then why is this M here? Because you might in the first lap or second lap or third lap or negative lap. It depends on where you. Okay. Well, one easy flex is you can try and show yourself. So if you restrict your projection map to this region here, right? It should be a homeomorphism. Okay, because what? Because you are not coming back to the same place. Okay, so you get a whole bijection. Okay, so we will then denote its inverse by inverse. Okay, so the whole projection map, there's no inverse map, because what? For example, a point 1 you can send to the multiple of 2 pi. Cannot. But if you restrict to a interval, it is bijection. Okay, you restrict the domain, it becomes a bijection. So how are we going to set our leaf then? Okay, so to show existence, one way is you give me the answer, how you define this leaf. So, well, let's define some leaf that makes sense. So if x is in A, what we're going to take is just f tilde itself. So I'm a big abuse of notation. Use f tilde to define tilde. Hopefully you know what am I talking about here. Because this f tilde is the leaf of A given already. Okay. And then how about all the point in B there? Okay. There's one very useful inverse, right? Use this inverse. This inverse is a homeomorphism. So this is exactly the reason why we want to miss one point. Once we miss that point, we got an inverse. Okay. Then we slowly build up. You can imagine or not, this thing can be done inductively. Imagine you have more things to leave. So missing one point, you leave already. And then the other part, maybe missing the other point, but not P. But I still can leave that part and then slowly leave. Okay, later we're going to use this inductive thing. Okay, now it's just missing one point. Well, so now you need to check whether they agree or not, they connect or not. Okay, this map is continuous or not. Okay, so not that. Now we actually got two definition on where? On A intercept B. Okay, On A-intercept B, there are two definitions here. You can use P inverse, you also can use the given F tilde. Okay, for the separate part, they are continuous. I think should be okay. They're continuous because they are composition of continuous map. But on A intercept B, there are two definitions. So we should check here. Okay, we should check here. But by construction, okay, by construction, if you do the triangle thing, it actually commutes. Okay, F tilde commute with P because it is by construction, by definition. But P inverse is by construction. P inverse, you go back to F. You understand or not? Okay, so by construction, both of them they're actually leaf already. If you restrict F to A intercept B. Okay, and agree on X naught. Why? This one is pretty important. Why they agree? Why they agree? Okay, because P is injective. Okay, because P is injective here. Okay, because P is injective. Yes. Yeah. So here is a injective in the restricted domain. Because P, okay, the whole P cannot be injective. The whole P cannot be injective, the projection map, but only on the restricted domain. Okay. So what? So by hypothesis, because they agree there, and then the intersection of A intercept B is connected. So by previous lemma, by previous uniqueness lemma, so the two map agree. So F tilde X equals to P inverse of Fx. Okay, on angle CP. Okay, so this shows that F tilde is well defined. It doesn't go two places, it goes to the same place. Okay, now. P, yeah. So here important point here is P is injective in that region. So F tilde go where? P inverse Fx also have to go the same place. They're in that restricted region. Cannot. Okay. So next, note that since A and B are close, then we can use testing lemma to say that this whole thing is continuous. Okay. So lastly, F tilde is continuous by testing lemma. Okay, because you define something from the union, something out of the union. Okay, and then very lastly, it is a leaf of F. Should be clear. Okay, F tilde is a leaf, and then P inverse F is a leaf because P inverse F is. Okay, good. Yeah. Any questions so far? No? Okay, so this is very important. You miss a point, only then you can leave. Okay, you miss a point, you can leave. Okay. Next. So now it's very quite specific now. So we just consider continuous map from 0, 1 to S1. Okay. And then we pick a fixed one point in R again, such that F0 is equals to E to the IY. No. Okay, so this is the special why not we pick. So basically you are picking who are the pre-image of F0. Okay, of P. Okay, actually you are picking the pre-image of 0. Because you could have if you imagine the example map I gave you just now, right? The standard circle parameterization. At the point 0, you should have a lot of y naught. Now just pick one of them. You can pick 2 pi k, right? So pick one of them. Then the very interesting result here is there exists a unique lift, okay, corresponding to this pre-match here. Okay, so meaning you could leave, but depend on what is the pre-match. You will start there. You make sense or not? Okay, maybe I give you some real life examples. You got X1 here, right? 0, 1. For example, this morning I go for a run, right? 0, 1 is your starting time and end time. Maybe I just run 30 minutes, or 30 minutes is this one. I can parameterize, right? Divide by 30, then become 1. Okay. So, so what does this mean by this lift here? So this is almost like where you start your run. For example, maybe my friend, I run 3 times. I run 3 rounds. He also run 3 rounds. But we stop at different place. Is it possible? Is it possible? He run 3 rounds. I also run 3 rounds. But we stop at different place. Is it possible? Why is it possible? Yes, start differently. Okay. Maybe here is the podium. Okay, after I put my bottle, I jalan, I walk here. I start here. But then when I run now, when I start running, he already start running here. So that's why we start at different place. So this pre-match here, the F0 here, maybe his is F1 lah. Mine is F2 lah. So our pre-match is different. Or why not is different. So maybe here is why not comma 1. And then here maybe is why not comma 2, something like that. Okay or not? Okay. So also every 1 round, 3 round, but if you start at different place, you have different lift already. But the point here is this lift have to be unique. Once you fix your starting point, you run 3 rounds. 3 count 3, then end. Nothing else. Because it's continuous, connected, whatever. So there's no magic here happening. So once you know how to start, you have to run 3 rounds already. You cannot say I break, I run, I break, I run, I break, I run. Cannot. This is continuous. Okay or not? So it's unique. Once you fix where you start, it's unique. So this is a bit like your PDE or ODE solution. Once you fix your boundary condition, then it's unique already. Okay. Okay. So the uniqueness actually is proven using the uniqueness lemma just now. Suppose you have 2 leaves, but they have to agree at some point. I will fix some point already. Then they have to be the same. Now the problem is existence. Okay, existence. How to construct? How to construct here? Okay, the point is how to construct here is important. Okay, so for example, here got 3 rounds. Then this doesn't map our construction just now, the existent construction. The existent construction says what? You need to miss 1 point. Only you can leave. So how are we gonna miss these points? Okay, what point we can miss here? Okay, so this is the problem of this existent proof here. Okay, let's finish this existent proof and then we will break. Well, uniqueness as before. Since they must agree. Where? At py, no? Py to that point. Okay. Okay, and then so now we want to do existence. Okay, so to show existence, we need to use the previous lemma. So we first decompose our time interval. Okay, we decompose it. So how do we decompose it? We decompose it such that on each sub interval, the image of f misses at least 1 point in x1. Is it possible or not? Should be possible, right? You cannot have one interval that like forever fill up x1. Does it make sense? Does it make sense? Does it make sense? Um, let's say the usual one. Let's say the usual one. The usual e to the let's say the usual one. So e to the 2 pi it, right? Okay, to this circle here. 2 pi it or just it? It is enough, right? 2 pi I or 2 pi it? Okay, just use 2 pi it here. Okay. 2 pi it. Okay. So at this point here, they only coincide at let's say this is f t here. Okay, so they coincide at f0 and f1. Okay. So how you break the intervals? Well, you just break these 2 points off. Right. Break like this. Then they will miss point. Correct or not? Okay, so if I break like half, right, I think you miss quite a lot of point actually. Okay, you miss quite a lot of point. The other than one. Okay. Yeah. Makes sense, huh? Okay. So now, let's set a very special open interval here, v plus minus 1, which is x1 throw away 1 plus minus 1. Okay, so where's plus minus 1 here? So I hope this parameterization won't confuse you. I think in at least for the nodes until now, we are living in C. Okay, so it's a complex plane. So 1 is here. See, if you want to use the R2 parameterization, it will be 1, 0, and minus 1. If you use the cos and sine, cos theta, comma sine theta. Okay, so one of them is this way. Okay, missing 1. The other one is missing minus 1. Okay. Yeah. So this notation is OR. Or V plus or V minus. And so write it together. It's an O, not N. Okay. Then we're going to use the Lebesgue lemma that we introduced last lecture. So what's Lebesgue lemma here? The point here is about the compactness. Okay. About compactness, chopping out the domain such that it will live inside some open set. Okay, so now we produce 2 open set already. So now Lebesgue lemma gives us a finite number n such that for every I in 0 up to n minus 1, we are only 2-dimensional. So that's why there's only 2 tuple we need to care about. In. Not 2-dimensional, sorry, 1-dimensional actually. Okay. So we can chop up our close interval here because this thing is compact. Okay, we can chop it out such that every part after the map is just living inside one of the open set like that. Okay, either you live on the red one or either you live on the red one or you live on the orange one. Okay, so you alternate. No need to alternate also can. It's just to make sure that this whole piece, this whole little piece here will live inside one of the open set. Then if you leave one of the open set, you must miss at least one. At least 1 point you miss already. Okay. Because the largest you can stand is like everything. Okay, but you at least miss some point. So this is the way how we chop out precisely. Okay. It's not just by, oh, I think I can chop out because this example seems like I can do it. No, because it's the compactness help you to chop it up. Okay, compactness help you to chop it up. All right. Wait. Quit. I'm finished already. So it remains to prove that we can slowly lift. Okay, what do I mean by slowly lift here? So for every I from 0 up to n, that should exist a lift f tilde lifting 0 up to I over n of f. Okay, which start at the same point, which is f tilde 0. Okay, no? Okay, base point we should know how to lift, right? Because that's the point that I tell you. Why not? Okay, so base point we already know how to lift. For I equals 0, just set f tilde 0 to be y naught tilde. Okay. So how about how to leave the consecutive one? So suppose we already define f tilde on 0 up to I over n. Okay. Obviously, this I less than n. So by construction, what's the next part we're gonna leave? So next part is what? Not that. By construction, the next part either live inside V1 or either live inside V minus 1. Okay. So it must live in one of them. But in particular, this construction here, right? This V plus 1 or V minus 1 here must miss at least one point. Okay, either you miss plus 1 or either you miss minus 1. But that's fine. We don't care. As long as it miss 1 point, I'm good already. So from the last lemma, we can extend. Okay, we can extend the lift f to the interval 0 up to I plus 1. Yeah, no? Okay, so the whole idea was I use the bed lemma to chop up my domain such that it lives inside one open set. And then this open set is good because it misses 1 point. After you miss 1 point, I can lift. I build the whole lift. Okay or not? Maybe one more bonus, no proof. We'll let you try yourself. So one more bonus is we can leave a harder space. Yeah. Nowadays, the knots are too long until my good knots keep jam. You see, I cannot pull. You see, it cannot. This good knot nowadays not stable. 啊？什么？complain 最好，对对对，这个是 Asian 的 good 呢，Asian educated，要骂一下，要打一下才动。Okay, so where is it? Okay, here. So we not only can leave the interval, we can leave product of interval also. Okay, you should imagine I should chop out this cube and like that. Okay, maybe this is the suggestion of order you can take. You can go this way down first and then up. Okay. And then you can leave. This is important, but we won't do in class. You can try and do as exercise or your revision. So this way, who do the revision duty? Larry, okay, you can start type the graph already, and then try and fill in the blank, fill in the gap. Hopefully, I think draft from Eric will come out soon, and then he will provide the sample in that case. 还没有发，可以，我们有一个时间的 grace period。Okay. Yeah. So 1 week to type everything, 1 week to do the exercises. Okay, to make sure you really understand what I say. Okay, because something I say, because those gap, let me tell you the true thing. I don't want to hide, but most of them I know how to do. And so I want you to try first. Okay, if you don't know, and then we can discuss in the office hours. So my office hours start officially this week. Okay, so if you have anything, you can find. Okay, so it's today 2 to 4, and then Wednesday 8 to 10. Okay, so officially start this week, you can book time. So this revision, right, it's not like a one person job. Actually, it's all of you, but I want to like quantize it, quantize. So I don't check whether you guys do revision or not. So that's why we have this duty roster. Okay, any questions so far? Live very important. We're gonna keep using this. Okay. How about we? So I'll bring your quiz every week because here contain your target. So if you forget your target, please come and look it. Refer back, okay? Remind yourself. Okay. Okay. See you. Not see you. Take a break until 10:10. Yes. 什么？哎，Ivan 呢？Ivan 他上个礼拜生病啊，这礼拜我不是。Yeah。Ivan 还没有看到，后天就没有车，他说车被夹走。可以。哦，因为你的 definition 还是什么？因为你这个不是可以拆成这个乘这个乘这个。如果它 abelian 的话，那三个东西是活在一个 abelian group 里面嘛？好，对，whatever 啊，两个都是它 abelian 又不是那个哦，为了有三个，这样的话就确实。哦，这样我上次要解释就是一模一样，为什么不是很多？因为真的，因为你应该可以再做多一点事情，是不是？你可以走过去，走过去，你做多一点，你走回来嘛，再走回去。那边在哪里先？那明天在这个 SE，在 S 零没有啦，没有啦，它整个哦 S 零。看你写啊，它的 image 是 ambient 就像是，I mean 你要刷等于对不对？我觉得你直接算罢了，我觉得直接算吧。如果 alpha，关系哦，它 ambient 啊，并没有在 S 零打那个，因为它肯定是发生，等一下，你在这边嘛，alpha 嘛，你一定是可以 OK，你要说两个等于嘛，肯定就这样子嘛，对不对？所以你就反这些嘛，这个是这个差这个差这个嘛，对不对？And then 这个是这个差这个差这个，用什的？OK，and then I think here is the magic. So I go alpha, and then I go beta inverse. 回来了是不是？再给它回去，看到了没？看到了没？看到了没？看到了吗？
这个真那个
要看到吗？是诶，
啊，
这样就可以了，因为它是 loop 的，那 abelian 嘛，对不对？最后跟第一个就会改变色，对吧？再写多一行，
哦，
对吧？对不对？
这一步要背的。
嗯，
你是在说这一步？
啊，这一步要对，你要加进去是不是？这个
啊，
这样，对，哦哦，因为 alpha beta 是
image
alpha
sub，
beta，
你要看看我换拼词的东西。
你是
现在
转错位了那个，
哪一个？
是应该跟那个转呢，应
哪一个？
该是 beta 乘 gamma 乘 beta inverse 乘 alpha beta inverse。
哪一步？
哦，beta alpha inverse 也是可以哦。对啊，对啊，对啊。
两个都可以，其实。我回去看了，是不是很长啊？
那也可以。不过我有想，我
几页了？
其实想问这个地方的那个图，
哪个图？
总觉得怪怪的。
哪个图？
就那个，就刚刚那个 proof 的图，
看一下。啊，那个 pro 在这边，pro 可以几页啊？13页。
3页是谈到目录的，你可以看看效果。不是刚刚那个 proof，上次就你不是你跟 A 站刚刚讨论的那个，
哪一个？
你跟 A 站刚刚讨论的那个，对，就那个，
好的。
什么没录到？
我跟 A 卷讨论什么？
这样很上面吗？
其实刚刚昨天、前天、3个礼拜
没这个图，这个，
啊，就么？
标的东西怪怪的，我怎么都看不懂。
为什么看不懂？走 A 啊，走 delta，走 A inverse 什么问题？
你的 alpha、delta 和 alpha 你们是连着的
你是说？
，delta 不是里面那条绿的吗？
是，就是来，我要把它想象成是一个 loop。OK，当然说这个位置如果不 homotopy 的话，这样的话是错的啦。
OK，
因为如果 homotopy 的话，就可以，诶，也不可以这样画哦，也不可以，也不可以。只是我想要，好，不可以，你不要这样画了。但是要怎么看呢？这样子的话，我是说来，这样你画贴一点哦，你画很贴，有什么意思？就贴在旁边了。如果你开，就感觉有点像分开了。
对啊，
但是你就很贴哦。但是我呀，很贴哦。
哎，其实而且这个地方应该不是放 L delta，应该放伽马吧？
哪一个？
这边应该放伽马吧？我觉得这个放到 proposition 下面比较合适。
有，可以随便随便，你
OK，
自己看一下，你觉得合理，你再给我看，我觉得合理就好。
你这 SE 啊
什么？
，SE 是有一个点重点，
什么叫 S 有
你骗我？你什么 Mac 啊？它肯定没有点重叠啊！不是讲那个 Mac 过后的点重叠，它自己那有什么点重叠？自己就是自己的点，对吧？我们只是 Map 了过后可能会有重叠，是来那个 mapping。哎，你很帅，都他们有没有跟你讲过？我死了啊！你们那时候有空吗？你都是知道这个东西的，只是说来，反正你是说要他不印度要什么什么，他知道，我们是有来，OK，这样子想啊，这个东西是他们叫我去负责的，因为我是那个阿米是阿米，me like Matthew，我们来签署，他们的品牌都对了，也那几个。maybe 有几个 section 啊，maybe 我猜啊，我还没有跟他们讲，如果时间 OK，我就跟他们讨论一下。I think 会有一个 section 是来介绍他们的情况，第二个 section 应该是他们想要来玩的玩的几个图玩这样，问他们。 我的 idea maybe 是来那个 briefing 后，可能就有兴趣跟你在我会在文章，来信息的啊OK 吗？这样我就口分一下那个是拜一来，你们有课吗？Most of the student I mean like after 用法法的是需要对那个 research 到那个时候，research 靠其实这个先放去拜信上了。所以不是晚上的，不会是晚上，不会这样。我这样的话，我就跟他们给你分别先了，你挑在我考虑。好，呀，下午咯，下午。可以啊，下午就给那个 deck 了，I think 是个 Monday。今天你 iPad 做好了吗？啊，还没有。558，所以你说他修完过后才可以空分多少钱？check 要钱啊？太超市。
他的菜单会不会有问题哦？是为什么那个我这么爆炸，好像是爆炸都烧坏了。要用早发那种餐厅，要用早发那种餐厅投，因为我的事情不健康。
嗯，没有吗？U Green。哎，我也是用外面的哦。有时候会这样。你是擦过龙吗？也没有，我还差3个东西，太麻烦了，戴太多头啊，每次我就戴一个头啊。
我自己在去飞了，可是你也可以这样洗，老是头上，然后讲我就大厉害。
嗯嗯，你会擦着用？是啊，我也是哦，我也是。哦，一边擦一边擦，我也是。可是你这边擦一边洗，会不会觉得好像有时候会手电这样？把那个线会，但是会不会手电？我有时候会手到哎，哎，手一下，手一下，手一下这样啊。OK，
他那个你觉得外面那圈
外面先去掉，然后呢？我觉得是这样，我们就沿着它旁边这样子画，你懂什么意思吗？就沿着它旁边。他们不是用那个 latex 叫什么 matcha 这样子画，这样就好了。分页，跟那个 matcha 这样沿着画就好了。分页，
OK，
那个 not 啊，那个 not 为什么？
啊，很好用，
哪个脑？
这样用
我会用啊，就是
很难用，为什么？
你要画
然后呢？那个 package 帮你做了什么事情？
那可死是
美化，这样
帮你做 face washing，
哦，processing
它会
啊
自动 processing 给你了，
，OK，然后其他还是普通的用 text 画的
你那计划
哦，是
它那个
喂，
这样用 matcha 咯，
就发现
嗯
在有点情
啊，OK，
只是用麻椒画脸上，
因为不是用笔画出来的，嗯啊，笔画，
手在美，
哦
是的话，笔触了，
，OK 啊，我看到你画的东西
那笔触可能比较
，B2 是什么东西？B2
两个圈，然后两次。
那个 borrowing 啊，诶 borrowing 那个，哦，绕两圈。诶，可是那个不是就有 crossing 了吗？也不是要用那个 package 啊？
做换，变成
还是你去找一下看他们讲话，可能有更好的嘞。啊
这样的control，那你
，OK，
它只是你要特你的 control 你要放点在那里，然后因为它是没有手环，对啊，是不什么不 accurate 啊，
OK，
我发现这样换很多次。
OK，下次你可以 share 给我，明天也可以 share 给我。Okay, let's continue. I think we have reached our most important theorem in this section. Yeah, 那 lemma 很好用哦，可以用在不同地方。Okay, well, so here is the map. Okay, we're gonna build a map between z and pi 1 of x1 fixed at one point, z not here. So z not here, there's a specific parameterization here. We call it e to the 2 pi I t naught. Okay, we just fix one. So this t naught is very special. We don't simply pick t naught. So this t naught here have gone to the left. Okay, so given any map to x1, okay, your list should start at the t naught. Okay, so meaning just now I told you, right, using the e to the 2 pi I t, k 2 pi is get sent into 0, right? But now we fix one t naught. Okay, if you want to fix 0, you fix 0, you want to fix 2 pi, fix 2 pi, fix negative 2 pi. So all your lifts should start at the same point. Okay, start at the same point. Okay, your lift should start at the same point here. But by the previous lemma, right, once you fix this starting point, your lift should be unique. Okay, your lift should be unique here. And then, so what's the map here? So these two are groups, so they are group homomorphism. We want to show it. And then in particular, there are inverses of each other. Let's see, inverses I think is easier to check. But the thing you see here is a lot of equivalent classes. So meaning what? You need to check well defined. Okay, well defined is very technical here. So first map is from Z to pi I. So what's the map here? What is the n here? Okay, we have been talking about this already. This n is like running how many laps. So how to define this how many laps here? Is actually t to the e to the 2 pi I n t. So this 2 pi I n t here will tell you how many laps. Why lap? Why? Why? It's like what I told you just now. One is like the ending point. But if I put 2 pi n here, it means it ends at 2 pi n. Okay. So you start from 0 up to n times 2 pi. Okay, the timing become your laps. Okay, how many laps you run? Okay, the timing become how many laps you run. How about the other direction? Okay, you start with homotopy classes of loop, okay, send to Z. So again, it's the same thing. You count how many laps you run, but how to count? Give you a path already. So you just take a starting point minus the end. It will tell you how far you run. So you might be curious, no? Hey, why this thing is an integer? Why this thing is an integer? Okay, this difference is not integer. You need to divide by 2 pi. Only divide by 2 pi is an integer. I think you see this kind of construction in complex analysis. You see it? Divide by 2 pi becomes some integer. Okay, so this is something about loops. So this is a property about loops. In the complex analysis, you also do the contour thing, right? That's a loop. Actually, that's where algebraic topology start, you know. You loop around the what do you call poles, around the poles, right? Poles is a hole. Okay, you look around pole. Okay, you walk around pole. Isn't it? RS say there's a, what do you call that? Branch cut, branch cut, right? You go around branch cut, you go to the next level. This level is exactly the lifting. Then you go to the next leaf. You go to the next leaf. You go to the next leaf. Okay, now. Okay. Right. I think the most technical part for this proof is well defined. Let's see where's to start here. 哪里？写吗？我呢没有 proof 什么？有啊，好长哦。There are two kind of proof I put. Yeah. Basically, if you look at the two proof inside the notes, right? Actually, they are very similar. Okay, they are very similar. They are using a similar argument to tell different story. Okay, let's use the first way. Use the first way. Okay, let's use the first way. So for simplicity, yeah, this one very technical. We won't go through everything in details, but something I want to point out. Let's go to the simplest case. Z naught equals to 1, and then we just pick the simple pre-image, which is 0. Okay, we don't want to go different 2 pi. Other 2 pi, huh? So there are a few things to do here. First thing is check they are well defined. Second is check their good homomorphism. And then third thing is to show that they are isomorphism. Okay, so this constitute all the proof. So let's do homomorphism, and then I'll to show you how we use the lemma. So let's first show that theta. First, let's show theta from pi 1 x1 1 to z is well defined. Okay. Right. So what to do here? So theta is which one? Theta is the counting the difference between starting point and end point. Okay, we know that their starting point is the same already. Okay, but we want to show that their endpoint is the same. Okay, we want to show that their endpoint is the same. Starting point we know is the same because every leaf should lead to the same starting point. Okay, so we want to show that for every alpha, beta, be 2 loops in x11. Okay, if alpha, beta homotopic, and then alpha tilde 1 equals to beta tilde 1. Yeah. Okay. Delta, I mean, alpha 0, alpha tilde 0 and beta 0, beta tilde 0 are the same because all of them are the same, lead to the same starting point. But ending point, okay, we want to show that they are the same as well. Okay, if they are homotopy. So in this case, we should involve the homotopy, lift of homotopy. Okay, so this is the point we introduced the lemma just now. So first, because they are homotopy, so we have a homotopy between alpha and beta. Then we can lift this homotopy up. Okay, so lift it to R. Lift to F tilde. Okay, this is by the previous lemma. Okay, we skip the proof. Okay, so note that. What's the analysis here? So next, note that F, the without lifting one, F1t is equal to 1 for t. Okay, makes sense or not? Because it's a family of paths that have the same base point, right? Okay. Thus, in turn, so what's the lift? What's the lift? This leaf should live inside the pre-image of P, right? Pre-image of 1 is what? We keep using this fact, huh? So this is a multiple of 2 pi. Okay, so this is a pre-image of 1 under P. Okay, so again, it is a connected space to a discrete space 2 pi z. So it follows that the map that fixing T to this leaf is a constant. Okay, it's constant. So constant, what to do here? What's the nice thing about constant? Throughout T. So if you check F tilde 1, 0 should be equal to F tilde 1, 1. But what is F tilde 1, 0? The S variable is 1. The T time is 0. So which family of path you are picking? Alpha tilde 1. Okay, the other one, beta tilde 1. Okay, so the endpoint is the same. Good. Good. So this one done. Okay. What's the next part I'm doing here? Let okay. Because this gamma a bit hard to think about what is starting point and end point, you know. It's hard to think about starting point and point for random gamma. But there's one path that's make this formula clear why we use this, which is the special path Wn. Okay, this path is special. Okay, can you see why is it special here? What's the leaf of this map? If I fix my special case, right, this is the example that we started when we start the class. Okay, what's this leaf? Who leaf to this? T to the 2 pi n t by nt. All right, by nt, huh? Okay, so this for this path, this value is very easy to calculate. All right, time equals to 1. What is it? 2 pi n. Time equals to t then 0. Okay, starting point is always 0. So it's 2 pi nt here. So that's why divide by 2 pi. 2 pi is a constant. Okay, so if this, because the nice thing, another nice thing about this is this gamma is a homotopy class. So what we're gonna show next is this loop here will always homotopic to some omega n, this kind of, because you must come back one. You need to remember, I go out from what point, I have to come back at that point. So this kind of path, every time should count how many rounds you run around this next one. Okay, we're gonna show this fact here. Okay. So let gamma I to x1 be a loop at the base point 1. Okay, you run to base, run from base point 1 and then run back. And then there will exist a lift gamma tilde starting at 0 and ending at some n in z, since p of gamma tilde 1 is gamma 1, which is 1. Okay, so we already know there's some n that can be achieved by this p tilde here. Okay, but there's a standard path also do this. Okay, another path. Okay, there's another standard path in R, also go from 0 to n. Okay, this is in particular our omega tilde. So do you know how to build homotopy between these two paths? This guy happen in R. Okay, these things happen in R. R actually is a convex set. Okay, so what you can do is you also use the linear homotopy. Okay, linear homotopy is your good friend, you must remember it. First thing you should do is try to use linear homotopy. If cannot, then use other. Okay, but this is a live in where? Where does this happen? Where happen? Where this thing happen in R, but our homotopy need to live inside x1. Okay, so what you can do is you can project it down. Okay, composing with P give a homotopy between we call F or gamma A. Okay, so gamma is homotopic to Wn. In particular, the homotopy class of gamma is equals to homotopy class of. Okay. Okay. Make sense? Okay. Why we want to do this? You might think that 反正我都去到一个 n 了，为什么不是 Wn 呢？ You might imagine this gamma n 我不是跑匀速的嘛 ，I'm not running with average velocity。反正我跑了嘞，累了，看走一走没有，然后再开始跑，再走一走，对不对？但是我还是跑3000的，所以你要小心啊。做运动是这样哦，你跑跑停停，跑跑停停，跑跑停停啊。Although you do the same thing 啊，你不一定做到运动，你知道吗 ？You understand 吗 ？You must keep your heartbeat at a certain rate， 你才可以开始烧你的 calorie， 知道吗？你跑3000跟人家跑3000很有可能是不一样的东西，你知道吗？你可能在那边走了1800。You understand or not? Okay, although their homotopy is really different. Okay, all right. 这个是这个 and then we shall do the other. How about I leave the other well-definers? Okay, because there's one more interesting stuff to show you. It's about homomorphism. Okay, the other well-definers I just left it for you as homework. So another well-definers left as homework. Okay, I want to show this homomorphism. This one is very interesting. I think you also never see. So let's show that the big phi here is the homomorphism. For this part to be homomorphism, I think is quite obvious. I think quite obvious. Maybe you try and do this. I think it's quite obvious for this homomorphism. But the other side is very interesting. Okay, let's do this one. Okay, so to do this homomorphism, let's first define one translation map. Later, we're going to use this. So x to x plus m. Okay, for m in z. Translate. All right. So let's do for the big phi here. So this capital phi here will go from z to pi 1. Yes. Psi 我没有圈它是吗 Psi, okay, thank you. So pi 1 of x1. So this psi here, capital psi. Psi. Okay. Okay. So okay, we're gonna do this. So psi m psi n equals to psi m plus. Okay, here is plus n. Okay, so this is our goal here. Okay, so what is sine m and sine n here? So by definition, it's just composing omega m and omega n. Okay, so from the previous previous calculation here, right? It makes sense for us to define this map n to just omega n, because every because every loop in x1 is just some omega n. Okay, so it makes sense for this map to define like this. Okay, well, so how to show this? Well, we can pass it back to leaf first. Okay, let's pass it back to leaf. Okay, this makes sense. Okay, you are projection of some lift. Okay. Projection of some lift, but if I want to concatenate them together, on the lift level, they might start with different point. Okay, on the lift level, they might start at different point. It makes sense or not? One is M round, one is N round, right? But now I try to mesh out on the lift level because one of them maybe start 0, the other one start the other point. Okay, to make sure they start with the same point, what we're gonna do is first I round N round first. M round. Okay, M round. I think there's something wrong in my notes. Then the next one is what we're gonna do is we start from the M round end point and then start running again. Okay, makes sense. Okay, only this. This is half, right? So like this. Can I do this? Let me think. Okay, this. Okay. So then only then we can compose the lift. Again, now we can compose the lift. I run M round and then I go to the M round and then I run N round. Okay. So this is how many round you run? M plus N round. Okay, so there's a technical part here. Okay, only now you can put together. Okay, all good? All good? Okay, so this is homotopy to P0 on omega M plus N. Okay, isomorphism is easy. Okay, you can show they're inverse of each other. You do one first and then do the other. Okay? See? 什么？没有，我们现在有太多东西要做，所以我们不可以全部做掉。我们要选最重要的出来做。有看过新的 idea，我们要选出来做。我要 define 就是每次都是 show 我的 define。Yes. Question. Yes.
就到第二个等号是什么等号？
这个 is similar to what we have shown for this gamma tilde thing. So you identify that the first map is running M plus N round, and then there's a homotopy between these two. Okay, using this you see this gamma here is just a random gamma. The previous argument when we show gamma is equals to some omega n, you need to appreciate this argument here. It's the same argument here. You understand or not?
为什么那三号compose起来会是
Yeah, so that's the thing. So you need to understand why this tree composition here is a path that run M plus N round. You need to understand this. Why we can compose it. You understand? 对，但是你现在知道你要知道什么吗？你要知道什么？你要知道它为什么会可以 compose。OK， 有很多东西你要知道。第一个你要知道的东西是为什么这个东西是 M plus N 的圈。你要知道这个是不是？然后你就要问为什么这个可以合在一起？为什么可以合在一起？为什么不要 WM 直接和 WM 就好？对吗？对不对？对吧？为什么我不要直接和 WM tilde 跟 WN tilde 嘞？因为他们两个的起点是一样的啊，你不可以合啊，你一定要推走它。你怎么推呢？你就要用 WM tilde 去推它哦，对不对？你要 start with WN 的 endpoint 哦。OK， 怎么选 WM tilde 的 endpoint 呢？就是这个 shifting map。OK 吗 ？Because WM tilde is a standard 圈圈。OK。Any question？还有吗 ？OK 啊。Yes。
S1 上面
Yes。Yes。
它是不是只有一个吗？
每一个 loop 都有一个 homotopy class 啊，对 ，OK， 然后 S1这边然后就每一就等下给我讲一下你在问什么东西每一种 loop 都有一个 homotopy class 这样子
在 S1上
对，没有错。S1 上面哈，可以我们再走一个 loop 你看。S1 上面你就跑
左右左右
不然有一天我们去跑步
这样你
哪一个？你要这样？你要这样这样我们就是讨论了早上嘛，这个是 contractible 嘛，这条路。刚才我们讨论了这条路 contractible， 是这一圈不 contractible， 所以你跑步记得不要这样跑没有开玩笑。
所以
这样还有两个路，就一种路喂，这个问题不 precise， 不知道在问什么。哪一个 ？OK，under homotopy， 这个蓝色的 loop 是 trivial loop。OK， 转来转去什么意思？转一圈就一圈对，但是我可以转两圈我可以转两圈我可以转两圈，来的，不一样的 loop，homotopy class 不一样。Yes， 三圈就三圈的 homotopy。这样 negative 圈的 homotopy 什么呢？
就我们定 starting point
等一下，negative 的 homotopy 什么 ？negative 的 homotopy class 跑另外一圈反着跑 orientation。Yeah，
定一个 starting point
我定一个 starting point， 每一个 homotopy class 就一个 loop， 对。为什么叫每个 homotopy class 就一个 loop？ 每 homotopy class 里面很多 loop， 我给你很多 loop， 但是homotopy class 被 classified by Z， 要这样讲的话 ，classified by Z，by lets by number of lets，
就是我们来转两圈的
不会 homotopy to 转三圈的。
所以第一个 starting point 只有一个东西能转两圈，你只有一个 loop 就是从那个点开始转两圈。
Yeah，
所以你一个翻那个 loop，
这是 under homotopy。
所以这样你的 homotopy class 里面只有一个 loop。
不对，不可以这样讲，不可以这样讲，它有很多 loop 在里面。
所以说我讲定一个 starting point，
不是你这样子讲错了，因为有一个 class 里面肯定有很多东西的，但是我们现在想讲它是 classified，
然后你可以
对，
跑三圈，然后再反着跑。
我们要讲的是它是 classified by Z， 就是说比如说一圈里面全部都会 homotopy to 这个正常跑一圈的东西，它不会有另外一个 class 了 under 这个 E 里面，所以我们讲 classify。
还有速度
有速度，
它都
可以跑，你跑然后再跑。
对就是加一些 contractible loop 嘛，加一些 contractible loop 进去。OK，
加一点 contractible loop 给我看。
好，那我就把这个拆掉。我的圈圈，我可以跑这样嘛，回来，这样，对吗？一圈呢？我只跑过来嘛，跑去。等下你不要跟我讲我去操场跑步会跑回来。来，anyway，这样就一圈咯，对吗？因为我可以把这段东西可以慢慢这样，对不对？可以吧 ？OK， 还有什么问题吗？这个很重要这个 concept。 very important。还有什么问题吗？还有什么问题？没有，暂时没有。再想一想啊，应该会有很多问题啊。supposedly，这是非常 new observation。I mean，不是 new 啦，but 就 in a different concept。Okay, let's prove one theorem as an application, then we can finish. So actually, this is a fundamental theorem of algebra. Okay, we're going to prove fundamental theorem of algebra. Every non-constant polynomial with coefficient in C has a root in C. Okay, so how to use this circle thing? Well, you want to make it to unique circle, right? So let's start with a random polynomial. So without love of generality, we just look at the monic polynomial. Okay. And right, we can factorize anything from complex number is a field. Okay, so we can factorize. And then that thing doesn't contribute to your root. Okay, so suppose it has no root. Okay, suppose it has no root. And then what happened here? Then we can do division. Okay, so for every r in positive real number, we're going to define this gamma PR. So this gamma PR here depend on P, so I put the polynomial here. Depend on R, so I put an R here. And then S is because our P also got variable, right? So this is the S. So what we're going to do here is P of R e to the 2 pi is. So it's like changing coordinates. Okay, over PR. Well, you might think, oh, why I need to divide by PR? Because if you do this later will be more apparent why we look at this. Is to make sure this actually constitute a loop. But we're going to divide by the length so that this is actually a loop inside S1. Hey, actually S1 is pretty important for you guys because the function analysis what they like to study function on circles. Okay. So after you go from real number, maybe the next easiest thing is circle. Okay, so this actually define a loops in X1. Can you verify or not? If you put S equals 0, put S equals 1, what do you get? Okay. Okay. All right. So in particular, actually, this is based at 1. 哎，针对刚才Adrian 讲我有点懒惰，不是？It's okay if I don't say anything here. I'm not purposely hiding something but you can ask me back. Okay, if you don't understand the thing that I miss or the thing I asked you to do homework. The point is I want you to try first. I want to see how you get stuck. And then I can have a better answer for you. Otherwise, if I throw another explanation, maybe you are not happy about that explanation. I also waste my time also. Correct? You 懂我在讲吗？
我想问你这个
Yeah
这个 balance
哪里？
这个东西 define 的 loop
这个 P 是用那个 P z 做出来的，因为我不会遇到0嘛，我不会被0 define，就是这个整个东西是 well defined。
为啥
OK， 因为我 define by PR 嘛，如果 PR 是0，我不是不 define 呢，对吧？它是 non-zero 嘛，so that's why I can always make it 1 by scaling。OK， 对啊 ，OK，so actually 这里还有一个很 special 的东西，其实a family of R here right actually is a homotopy。可以 imagine 吗？ Imagine or not? Is a homotopy. 如果你把 R 送去0 what do you get? Yeah, any something 啦，不知道什么来的 but something. So it's a homotopy between gamma 1 and gamma 0. Okay, it's a homotopy. 什么？ 如果伽马可以是零，伽马可以是零。伽马是零的话，就是 P 零 over P 零，P 零 over P 零就是 E 咯，全部都是 E 是吗？Yeah, okay. Yeah. So actually gamma zero is a constant part. Gamma one 是 something else，用 P 做出来的一个 loop。Okay. So since gamma zero is the trivial loop, actually we can deduce that this class here, the gamma R we deduce here, actually is 0. Sorry? 在哪里？就是说这个 R 变的话，它是个 homotopy，整个 family。Berry 是变。Okay, then where's the contradiction here? So let's build a contradiction here. Now let's fix a large value, okay, of R greater than the maximum, okay, of absolute A1 up to absolute AN and 1. Okay, either we choose 1, either we choose the sum of these AI. Then if you look at a point that is R away, okay, what we could have is using triangle inequality here, or first use the definition of our Z first. Okay, we can pull out one Z because Z is as R far, but this R is like far away than this sum here. And then we can use triangle inequality to push this in. Okay, and then finally we can compare with the this polynomial. Okay, compare with this polynomial, and then it follows that. Okay, so look at this polynomial here. Pt of z equals to zn plus t of 1 a1 z t and here has no root. Okay, has no root on the circle z, length of z equals to. I think this r is the big R. Okay. Why no root here? Because our distance of zn is always greater, strictly greater actually, okay, than the part at the back. Okay, so if you take the difference, don't get 0. Okay. Okay. So what's next? So what's next? So just now we defined this gamma R for a fixed P, right? Okay, so we also have no roots for PT, right? So we can replace this P, all these P by PT. Okay, replace all this P by PT. Then what we do was, so by replacing P by PT in gamma R P, okay, we get homotopy from the loop gamma R actually to the loop of gamma nx. Okay. Okay, so where's the homotopy here? Need to be precise a bit by letting t goes from 1 to 0. Okay. You see why is it 1 to 0? Look at this PT we define here. Very special PT. Yeah. Okay. So at 1 is a usual polynomial. At 0 is a Zn. Okay. We should end soon. Okay, is a Zn. Okay, this is the Wn map. Okay. So let's continue. So let's put everything together. Late. So we represent. So wait. So but Wn is equals to gamma r, but we show that gamma r is 0. So this implies that actually n should be 0. Okay, you are not looping anything. Okay, so in summary, what we have here, so we start with a static point, okay, gamma 1, E1, but this is just a gamma 0p, okay, but we show that it is homotopic to gamma rp, okay, then this is actually equals to gamma of p1r, but there's another homotopy, right? We show you just now by varying in t. This is homotopy to p gamma p0r, but this is Zn. So Zn is just looping how many rounds? Okay, so we show that Wn is just a point. Okay, thus the only polynomial, but this n is the Zn, no? So the n has to be 0. So n to be 0, Z0 is 1. So this means the only polynomial without root in C are actually constant. Okay, so this n here, the looping around, right, become the n in the polynomial, the degree of the polynomial. So the degree of polynomial must be 0. So z to the 0 is 1, is a constant. Okay or not? So the degree of polynomial, we divide by the length, become a loop inside x1, and then we deduce that this loop has to be a trivial loop. Okay. And so this is the whole idea. Okay, we should leave now. Any question we can answer on Wednesday.